Hi everyone. This week we're going to be talking about electric potential energy and electric potential difference. So these quantities are often very hard to understand. We have to consider the fact that the charges can be positive or negative. Changes in potential energy can also be positive or negative. So it can be a challenging chapter. What I will say is that if you pay attention very closely to the analogy that we made between the electric force between two charges and the electric field due to some charge distribution, right, being the force that would be present on a unit 1 coulomb charge, it helps make sense out of the idea of electric potential and electric potential difference. Okay, so let's get started. Pull up the slides. All right, so what is electric potential difference? Let's start by drawing an electric field. So I've got some charge distribution somewhere that I'm not going to depict, and that charge distribution has created an electric field, E, in the surrounding space. Now I'm going to take a charge Q, I'm going to place it in there, and I'm going to move that charge Q between points A and B in that electric field. And maybe I'll take it on a path that takes it from A to B like this. Okay, well, if Q is a positive charge, plus Q there, then the force that's acting on it at the position that it's in is Q times E. So I can draw that force. I know it will be parallel to the electric field line here. So there's the force acting on Q. And I've got this path, which is complicated, and it goes from A to B. But I can look at an infinitesimal element of that path, and I'll call that element of the path dr vector. Dr, being an infinitesimal element of the path, is by definition tangent to the path. So I've got a vector that's tangent to the path, and then I've got this vector f, which is not quite tangent to the path. They make an angle between them, which I'll call theta. So the infinitesimal amount of work that I do in moving the charge over that displacement dr, I'll call that dw, which is f dot dr. This is the scalar product, which is equal to the magnitude of f times the magnitude of dr times cosine of the angle between them, theta, cosine of theta. Okay, so now what about the work that I do in moving from A to B? I'm sorry, the work that the electric field does in moving from A to B. The work done by the electric field in moving from A to B will be the integral of f dot dr. I want to add up all those infinitesimal bits of work as I go from A to B, which is moving along this curved path. So the angle between f and dr is changing. The magnitude of f is changing as I move along. And this is what we call a line integral, which we often write with a little circle in there. So that's the work done by the electric field as the charge Q moves from A to B. Okay. Well, the electrostatic force is conservative. So that means that it doesn't matter which path I take. I could have found the work done in going from A to B this way, or I could have picked a different way to go from A to B. And the work done taking a different path would be exactly the same. Further, if I went back to where I started, I took a path that took me back to A, I would find that the work done in moving on a closed path is 0. The last part that defines a conservative force is that we can describe the potential energy, the work done in moving an object, or that the force does in moving that object, using a potential energy function. Okay? And for conservative force, the change in potential energy, what we'll call delta U, AB, is negative the work done by the force in moving it from A to B. Okay, so we can write down the change in potential energy now. Change in potential energy is negative the work done. So I just have to put a minus sign in front of my integral. Okay. And then we can start to define a new quantity that just makes this easier if you're going to do it a whole bunch of times. That's one way you can think of it. So what if instead of moving this charge Q, whatever its value was, what if instead of saying, maybe this is an electron, and it's got a charge of 1.6 times 10 to the minus 19 coulombs, and it's negative. What if instead we just make sure that we only move a positive 1 coulomb charge? So we'll say Q naught is plus 1 coulomb, right? Then because of the magic of using the number 1 here, what we have found is the work done per unit charge. And if I want to find the work done in moving a different charge of charge Q, whether it's positive or negative, I would just have to multiply that charge by the work done on a 1 coulomb charge, if we moved a 1 coulomb charge. So we're going to define delta VAB. This is what we call the potential difference. Potential difference is delta VAB is delta UAB divided by Q, divided by the charge that we actually moved. What does that mean? That means take the integral, and instead of using force, we should use force divided by Q, which is electric field, E dot dr. So the potential difference is the change in potential energy per unit charge. Okay, and we measure that in volts. Volts are the SI unit of electric potential difference, which is just another name for joules of energy per coulomb. And if we want to know the change in potential energy from a charge, as I said, change in potential energy is the change in potential, the potential difference, delta V times Q. Okay? So let's look at this example here and think for a second what happens. I take a positive charge Q, and it's initially at point A in the electric field, and I move it to point B. Moving the charge a distance delta R from A to B requires work QE delta R, right? And so what's happened? Have I increased the potential energy or decreased the potential energy? In this case, I did work against the electric field. The electric field wants to move the charge from B to A, not from A to B. So that means that the electric field did negative work, and I increased the potential energy. Okay? What if I move the positive charge from B to A? Then the electric field did positive work, right? And remember that forces always want to move things to lower potential energy. So you can imagine if I take a marker and I drop it, what does gravity do? Gravity pulls the marker down, right? The marker moved in the direction of the force, which meant that the potential energy went down. Okay? But what if I had a negative charge instead? If I took a negative charge and I moved it from point A to point B, the negative charge already wants to move in the direction opposite of the electric field. That is the direction of the force. And so that way, right, the way you see it, right? So that means that the electric field would have done positive work, and we would have decreased the potential energy if we moved a negative charge from A to B. Okay, so you see the difference between the charges and whether I'm storing energy or I'm losing energy. Okay, if you've heard of the electron volt before, this is just a unit of energy. So how is an electron volt a unit of energy? You might have noticed a volt is a joule per coulomb. That means a joule is a coulomb times a volt. And an electron charge, 1.6 times 10 to the 19 coulombs. If I take an electron and I drop it through a potential difference of 1 volt, then it will gain kinetic energy of 1 electron volt, or 1.6 times 10 to the minus 19 coulombs. Okay, let's look at the potential energy of a point charge now. So a point charge, Q, sets up a field in the surrounding space that points radially away from it, as you can see in the diagram. The magnitude of the electric field at a distance r away from the point charge is given by E, call that Q, is kq over r squared. It's the magnitude of the field. And it points radially away from the charge, right? Because the field is the force that would be present on a positive 1 coulomb charge. So that force would be away from the other positive charge. Okay, so now let's take this and we'll displace it. We'll move this charge from point A to point B, outward, away from the positive charge that's causing the electric field. That means dr is going to point this direction. We're moving it to the left. The electric field, that's E, is also to the left. I can find my change in potential, delta VAB. That's got to be minus the integral from A to B of E dot dr. Okay, well, the electric field, this is a scalar product. Just want to remind you, a scalar product says that's the magnitude of E times the magnitude of dr times cosine of the angle between them. So I've got the magnitude of E, the magnitude of dr and E are both parallel to each other. Cosine of 0 degrees is 1. So I can just plug in the magnitude of E and dr. I've got minus the integral from A to B. Electric field is kq over r squared times dr. K and q are constants. I've got dr over r squared, or r to the minus 2 dr. So delta VAB gives me minus kq, pull those constants out, then I integrate and I get minus 1 over r. Right? R to the minus 2 gives me r to the minus 1 divided by minus 1. That's how I picked up the minus sign here. And I want to evaluate that at A and B. Okay? So the minus signs cancel here, and I'm left with the change in potential energy is kq times 1 over rb minus 1 over ra. Okay, what do you think should happen here? Should the change in potential be positive or negative if we moved away from the point charge here? If I take two charges of like sign and I put them next to each other, these two, then the electric field the electric force is pushing them away from each other, right? Like charges repel. So in order to bring it in, I have to do work against the electric field, right? Which means the stored energy is increasing. And if I move them outward, then the stored energy must be decreasing. The electric field is doing work. So I expect that the change in potential energy is negative if I move this positive 1 coulomb charge, which is what I'm using to calculate the potential difference, from A to B. Okay, so what's bigger? Well, RB is greater than RA, but 1 over RB is less than 1 over RA, so that means that this is a negative number. This is a decrease in potential energy. And a decrease in potential. If I wanted to increase the potential, I would have to move from B to A. I would have to move closer to that charge. But if instead, if I wanted to find even though the potential would increase going from B to A, regardless of what's going on, as long as this is a positive 1 coulomb charge, if I wanted to find the potential energy in moving from B to A for a negative charge, then I would have delta U, AB, is Q times delta V, AB. So even though the change in potential energy, I should call those BAs. Let's do that, BA instead. Even though the potential energy would increase for a positive charge, that means the potential would be positive. I multiply by a negative charge if that's what I'm actually moving, and then the change in potential energy is negative, right? So positive and negative charges do the opposite of each other when you move them in the presence of an electric field. Okay, so finding potential differences using superposition. I've got this one positive charge here, but now I could also write down a potential function for a positive charge. And it's convenient to say that that potential function V of R for a point charge is KQ divided by R, right? So when we integrated, the terms that we got in our potential difference were 1 divided by R's, not 1 divided by R squareds, right? So our potential we can take to be KQ divided by R. And that gives us a natural place where the potential energy, or the potential, is 0. So V of R equals infinity is 0, right? As R gets large, then the potential decreases. So we can take as a place to have our potential be 0, we can take that to be infinitely far away. All right, so now let's say that I don't just have one point charge over here, but I have another point charge over here, and another one, maybe it's a negative charge over here. And I want to know what is the potential of a point at a distance r from the center of this charge distribution. What is the potential V at point P? Okay, well, since we're taking the potential to be from a point charge to be 0 at infinity, any sum of point charges, we can also take the potential to be 0 at infinity, as long as some of those charges aren't infinitely far away. As long as they're relatively close to each other, as you zoom out, as you get infinitely far away, then the potential should be 0. So that means that if I have a sum of charges, Q1, Q2, and Q3, that the potential at a point P should be the sum of the potentials due to each of these. So this will be K, Qi over Ri, and I'm going to sum over I. So I would use R2 is this distance, and R1 is this distance, and I can just add them up. Now, I want you to realize that this is a scalar. Potential energy is a scalar quantity. It is not a vector quantity. So this is not a vector sum. This is just a sum over scalars. We just add. Okay. Now, if I had a continuous charge distribution, suppose that instead I put some charge along a wire, so it had some charge density lambda, then I would just integrate. So the potential at a point P would be the integral of the potential due to a bunch of point charges. And we shouldn't have this go out to infinity. This would have to be a finite wire of length L. If it goes to infinity, then we're making a mistake. We have to change things. Okay, so what about the potential from a dipole? We just add the potential due to each of the point charges to get the potential from a dipole. And you can see a little three-dimensional example here. We can see that the potential is negative, close to the negative charge. The potential is positive, close to the positive charge. And it decays away towards 0 as we get farther away from either of the two charges. Okay, so let's check our understanding. The figure shows 3 paths from infinity to a point P on a dipole's perpendicular bisector. Compare the work done in moving a charge to P on each of the 3 paths. Okay, so which one do you think would have a greater amount of work done in moving a charge to P? Right? So the work done by number 1 would be the least, right? And moving towards the negative charge, and opposite charges repel. Attract. So that's attracting towards the negative charge. If I go along to the path 2, there's no work done, right? Because I've got an attractive force towards Q and a repulsive force towards, attractive force towards minus Q, a repulsive force towards plus Q. The two forces cancel. The net force on the charge as I move it towards P from infinity is 0. So the net work done is 0. All right, and the work done on 3, I'm coming in from more or less the positive charge direction. Positive charges, like charges, repel each other, so that will be the greatest amount of work that I would have to do. Okay. So here's an example of a continuous charge distribution, charged ring. We worked out this example with the electric field, so what would the example look like if we were finding the potential of the charged ring? Okay, so we have lambda, the charge density, was what we used for, was Q over the length. And what length do we use? We use the circumference of the ring, which was 2 pi a. Okay, and the integral that I have to complete to find the potential at point x, the potential at point P, and the distance x away, from the center. I should call that potential at P, not potential at X. Because, right. So anyway, that's going to be the integral of K dq over R. And I'm treating each one of these dq's as a point charge. As you can see in the diagram on the slide, R is the square root of x squared plus a squared. Okay? So V at point P is the integral of K dq is lambda times, call it dl, where dl is the length around, the length across the charge element dq. Okay? So if I have the ring, I'll zoom way in here, and I have this charge element dq. There's the ring, a piece of the ring. Then dl is the distance across that little infinitesimal element of the ring. So now I'm left with K lambda dl, that's my dq, divided by R. R is the square root of x squared plus a squared. And where do I want to integrate? I want to integrate dl all the way around the ring, so from 0 to 2 pi a. All of these are constants. The only thing I'm integrating here is dl. So I'm left with V of P is K lambda over the square root of x squared plus a squared. And I integrate dl from 0 to 2 pi a. I get 2 pi a. Now we can plug in our charge density lambda. That's q divided by 2 pi a. And the 2 pi a's cancel each other out. So I'm left with a potential at point P, which is kq over the square root of x squared plus a squared. Notice this is not the same as the electric field. The electric field at point P was kqx over x squared plus a squared to the 3/2. Okay, I'll let you do the disk on your own, and I want to go and talk about gradient, the gradient operator, and finding the electric field vector from the electric potential now. So we know that the electric potential difference, delta V AB, is negative the integral of the electric field, scalar product with between the electric field and dr along any path that takes us from A to B. And you probably have the idea that, well, wait a second, if I integrate to get the difference in potential, then maybe I should differentiate potential to get the electric field. And you'd be right. But the thing is, this is a case where we're doing the integration in 3 dimensions. And how do I get this directional derivative, this what we call gradient? So let's look at an example here. For example, we have a potential. Let's call it V of x and y. And I'll draw a V on the z-axis here. And I'll have a plane with x and y. And suppose that I'm, I don't know, maybe relatively close to the positive charge in the dipole case, in which case I would see that the potential drops off. Oop, well, maybe I'm not. Maybe I'll do a different case. Maybe I'll just have some lumps and bumps here. To make a general case, something a little bit more complicated. So here's my potential energy, and what does it look like? It looks like a mountain peak that's centered at the origin, and it gets smaller as I go further away. Well, this is something you probably learned in Physics 1 when we talked about force and potential energy, was gradient. So let's now look at, if I put a ball on the mountain here, the ball would roll down the steepest slope available to it down the mountain. That's the direction the ball would roll. That's because the object wants to minimize its potential energy. The conservative force of gravity wants to minimize the potential energy. So what direction does the ball roll? It rolls the steepest way it can down the mountain, whichever that is. Okay? And that is the direction of the force on the object. So if this is potential, and this is a positive 1 Coulomb charge here, then this must be the direction of the electric field. How do we calculate that direction? This is a vector, and this is a scalar. It's a scalar value at every point in space, but just a single value. E is a vector at every point in space. It's the arrow, which is the steepest way down the mountain at whatever point in space that is. So E over here might point this way. Okay? So in order to get that, I need to take gradient. And gradient is a operator that gives me the steepest way, the direction of steepest increase. But I'm really looking for steepest decrease. So I can write that E is not gradient, but minus gradient of V. This is a vector. This is a scalar. So what does a gradient, this upside down triangle, mean? It means take the partial derivative of V with respect to x, put a minus sign in front of it here. Call that the I hat component of the vector, minus the partial derivative of V with respect to y, call that the j hat component, and minus the partial derivative with respect to z, and call that the k hat component. So that is how we find the electric field vector, which has components, from the scalar value of the potential, which does not. Okay. We can also draw equipotential lines. Equipotential lines are lines of constant potential. So for our mountain here, those equipotential lines would be like this, and they are, as you can see here, they are at right angles to the electric field. Okay, so electric field always crosses equipotential lines at right angles. That means it takes no work to move along an equipotential line. The electric field does no work. Okay, what about charged conductors? There's no electric field inside a conductor in electrostatic equilibrium. And even at the surface of a conductor, there's no field component that is parallel to the surface. So a conductor in electrostatic equilibrium, its surface is an equipotential, and the equipotential lines follow the contours of the surface near the conductor. Okay, so electric potential difference describes the work per unit charge involved in moving a charge between 2 points. The SI unit is the volt. Electric potential always involves 2 points. So when you talk about volts, you talk about the voltage or potential difference between 2 points or across some distance, not the voltage at a point, right? The voltage at a point must be with respect to somewhere else. The potential, anyway, so for a uniform electric field, the potential difference is delta VAB is minus V times, or dot product with the displacement delta R. So if we have a continuous object, we can find the potential due to that continuous object, taking the potential to be 0 at infinity. We do that by integration of a scalar quantity, k dq over r. And we can find the electric field if we know the potential and the potential function just by taking the partial derivatives times the unit vectors in those directions. And so before I quit, I wanted to solve a couple of examples, or at least, one example. And this one is find the potential difference of a point B relative to the point A in the vicinity of an infinite wire. So here, this is a maybe slightly confusing problem, because with our infinite wire here, there are points at infinitely far away, where we have charges. So we cannot say that the potential as R goes to infinity equals 0. No way. Sorry, my cat's being annoying. Let me open the door. All right. So we can't do that, which means that we can't use the formula that V at point P is the integral of K dq over R, right? We don't want to use that in this case, because we can't say the potential is 0 at infinity. So what can we do? We can say that the potential difference between 2 points, VAB, is the integral minus the integral from A to B of E dot dr. This is the equation we're going to use, and we'll use this to develop an equation for the potential from an infinite wire. Okay, so let's put a charge density plus lambda on the wire, and we want to know what is the potential difference of the point B relative to the point A. So we have a point A, and a little bit further down the road we have a point B, right? And the electric field due to the wire is everywhere outward. Okay, so that's the electric field. And we solved for the electric field in the last chapter for an infinite wire from Gauss's law. And before that, using Coulomb's law and some annoying Coulomb's law integrals, we were able to find that the electric field as a function of R away from this wire is lambda over 2 pi epsilon naught R. That was our electric field from an infinite wire. Okay, so we need to plug that into our integral here, and when I do that, I get VAB is minus the integral from A to B of lambda dr over 2 pi epsilon naught R. What happened to the dot product? Well, I'm moving in this direction from A to B. There's my dr. The electric field is in the same direction that I'm moving, so the two are parallel to each other. The angle between them is 0, cosine of 0 is 1, and I just have to multiply their magnitudes. Okay, I can take all of these constants outside, so I get minus lambda over 2 pi epsilon naught, and the integral that I have to calculate is dr over R, and that is natural log, right? So I've got VAB, the potential of B, potential of B with respect to A, that's VAB, okay, sorry, delta VAB. It's the potential of B minus the potential of A, which is the potential of B with respect to A. That's got to be minus lambda over 2 pi epsilon naught ln of B divided by A. Okay? Or since natural log of, this is natural log of b minus natural log of a, I could also change this minus sign to a plus sign and write this as log of a over b. Okay. So, what if I wanted to find the potential, a point, let's say, where I want to call the electric potential due to the infinite wire 0? Should I say that that point is at infinity? Well, let's call our point of interest R here. Okay? If R goes to infinity, then this goes to 0, and ln of 0 is undefined. That's not going to work for us. What if we say at 0, right? R equals 0, well, then this becomes undefined. So that's also not going to work for us. So we can't say that the potential is 0 at infinity like we did for the point charge. We also can't say that the potential is 0 at 0. So where do we pick for the potential to be 0? We'll just pick some arbitrary point. How about point A for that matter? We'll say the potential at point A is 0. Okay? So then this would be just A over R. This would give us the potential as a function of R for the infinite wire. Okay? What I want to explain to you is that the potential itself doesn't matter. It's differences in potential that matter. Forces cause objects to experience differences in potential, right? But remember, when we did this with the dipole, if I take my marker and I put it on top of a table, I can say that it has 0 potential energy on the table, and that it has negative potential energy when it's below the table. But I could also say that the 0 of potential energy is when it's down here, and that it has positive potential energy when it's on the table. All that ever matters, though, is if the marker goes between one point and another point, the potential energy changes by a certain amount. And the change in potential energy, U final minus U initial, is the same regardless of the starting point, the point where I say that the potential is 0. Okay? So it's arbitrary, and we can set our 0 of potential to be anywhere we want, including at point A. Okay. All right, so that's all I got for this week. Next week, we'll talk about electrostatic energy and capacitance. See you next time.